Any more homework?
No more progressive.
I sort of have to keep giving problems.
Well, we already have problems.
Yeah. Okay, so well, we're going to just keep going through these problems that I think are sort of cool examples of this stuff. If no one has any homework questions, how's the workload been? Okay. Okay. Yeah, exactly. Yeah, I know what you're talking about. Although that is funny, but I want to discourage that attitude. I mean, I can't claim that I didn't do that, but my whole everything that I do in this class, in my classes, is designed to nudge you towards avoiding that approach. So that is what I try to do, you know? Yeah, I try to, the things that I look back and think like, I wish I'd done this and this. That's what I'm trying to, I do focus on those. Yeah. I don't know. I don't know. Busier? Well, yeah. Oh, yeah. Yeah. Yeah.
It's like, I didn't prepare it.
Mm-hmm. Yeah. Okay, so here's what we're doing. Okay, now I get to talk. What changes when a pulley has mass? You've always wanted to know this, and now you get to. Okay, so let's do so a pulley hanging from the ceiling. And let's say there's a 20 kilogram mass on this side, a 10 kilogram mass on this side. And we want to calculate the acceleration of the 10. So the 10 is going to accelerate up, the 20 is going to accelerate down. First, we'll do it with a massless pulley. We've done this many times, and that's just particle kinetics. And then second, we'll do it assuming that the pulley has a mass of 1 kilogram. That's pretty heavy. And a radius of 5 centimeters. And actually, if nothing else, this example, so something with a diameter of 10 centimeters, that's a pretty big pulley. 1 kilogram is a lot, probably unnecessarily big for this calculation. But you'll see that the difference is small enough that it's very believable that leaving out the pulley's mass is pretty reasonable in a lot of applications, you know. Okay, so free body diagram. So first we'll do it without mass, free body diagram of the 20 kilogram mass. We have a downward force of 196.2, upward force of T. So Newton's second law, you just think about the y component. Positive T minus 196.2 is equal to the mass, 20, times the acceleration, I'll call that A20. And so the first equation we'll save says T minus 20A20 is equal to 196.2. Set that aside. And then a free body diagram of the 10 kilogram. There's the weight, 98.1, and the cable force, T. The y component of Newton's second law says T minus 98.1 is equal to 10 times A10. They're equal and opposite, so we'll deal with that in a second. Yeah. So T minus 10A10 is equal to positive 98.1. Okay, so here we have two equations for three variables, which means we need a third equation that relates these things. We need another equation without adding any new variables. And so that constraint equation comes from the geometry. And it says that if you, so the relationship is if you pull this one down an inch, this one goes up an inch. So the velocity of this one is equal and opposite to the velocity of this one, and the acceleration of this is equal and opposite to the acceleration of that. So A20 is equal to negative A10. And I'll just substitute this in. Well, and I'll call A10 just A. Why am I doing that? Who knows? Let's leave that out. Okay, so now our system of equations says T. I'll substitute in here, so plus 20A10 is equal to 196.2. Our second equation says T minus 10A10 is equal to 98.1. And I'll subtract equation 2. And so you get 0 is equal to, no, that's not how math works. 0 plus 30A10 is equal to 98.1. And so A10 is equal to 3.27. That makes sense? Yes. Okay, so A10 is 3.27 meters per second squared. Okay, so the 10 kilogram is going to accelerate up at 3.27, and the 20 kilogram is going to accelerate down at 3.27. So now for part B, we're going to assume that the mass is 1 kilogram and the radius is 5 centimeters. So what this changes fundamentally in pulley problems is that you can't assume that the tension in the cable is the same on the two sides of the pulley anymore. So cable tensions on the two sides of the pulley no longer have to be the same. Okay, well, we're going to start with those same two particle problems. So I'll do a free body diagram of the 20. There's a weight force of 196.2. There's a tension force I'll call T1. Or, sorry, call that T20. So Newton's second law, if we only look at the y component, says T20 minus 196.2 is equal to the mass times the acceleration. So I'll call that, the mass is 20. I'll call that acceleration A20. Reformat it. So we have T20 minus 20A20 is equal to 196.2. And then a free body diagram of the 10 kilogram. There's the weight of 98.1. Cable force that doesn't have to be the same as that other cable force anymore. So I'll call that T10. And then the y component of Newton's second law says 0, the y component only. So T10 minus 98.1 is equal to the mass of 10 times the acceleration of the 10, A10. And I'll reformat that as T10 minus 10 A10 is equal to 98.1. Okay, so what do we have at this point? Last time we had two equations for three variables. Now we have two equations for four variables. We can still use the same constraint equation. We're assuming that this doesn't stretch. And so we'll still say that A20 is negative A10. And now we'll rewrite this system. We have the first equation that says T20 plus 20 A10 is equal to 196.2. And the second equation that says T10 minus 10 A10 is equal to 98.1. And now this is two equations for three unknowns, three variables. But we've already used up the constraint equation. So where are we going to get we need another relationship, and where's that going to come from? Pulley. So we're going to do a rigid body problem now with the pulley. So we're going to do a rigid body kinetics problem with the pulley. So we'll go through the steps. First one is you have to decide whether the body that you're dealing with has a fixed point or not. Does it in this case? What's the fixed point? Center. Yep. So it does have a fixed point. At the center. So the about point is the center. Now we have to calculate the moment of inertia of the body around its fixed point. So the moment of inertia about the center, we're going to assume this is a disk. I didn't say that before, but it's hard to imagine a pulley that's any other shape, really. So 1/2 times the mass times the radius squared. And so that's 0.00125, I think. Kilogram meter squared. And now Freebody diagram of the body we're isolating. That's the pulley. So what forces are acting? There's the weight force. That's 1 kilogram times 9.81, so 9.81 newtons. There's a force applied to the center of the disc by the pin. That's just an unknown force vector. I'll call that R. Then there's the two cable forces. Over here, there's the force T20. And over here, there's the force T10. We are still assuming it's not slipping. I've never really thought about that before. So that friction force, that is a good question. We're ignoring the friction at the pin. That would just come in as a couple. So we are going to, so here's how it is. You can think of it as like we're not really isolating just the pulley. Isolating the pulley and some amount of this cable. So there's a rigid body that contains that whole pulley and this stretch of the cable, and it's fixed together rigidly. So we're not including the friction in there, but because it all moves as one thing. So the fact that we can treat it all as a rigid body includes the idea of that friction in there. Okay. It's a weightless cable, so that doesn't change anything. We could do that. I wasn't planning to, but yeah. Maybe.
How does that change versus a bike sprocket that has a chain?
Mhm.
Because then it's not going to be the same as a cable.
You could do it. You could think of it the same way, as long as the weight is still negligible. It would still work the same. You could treat it like you're isolating that part of the chain in the gear. Okay, so now we have to think of the. So if we've already decided we have to put the about point there. And so think about the rho and the force and the moment for each of these.
So what does rho mean?
Was that just on the quiz?
Yeah. Rho?
Rho is the vector from the about point to where the force is applied. Yeah, P minus A.
Yes.
You know, I think sometimes it's helpful if you like repeat these things, these definitions you have to know, if you repeat them to yourselves in like a robot voice. Like to make yourself think that you're just like a hard drive containing this information. You need to get over the fact that you're doing any real thinking here. You're being taught algorithms and you're processing those algorithms. Okay, so rho equals the vector from the about point to the place where the force is applied.
What if we just write P minus A?
That's fine. Okay, so first let's do the two that are acting at the about point. Our vector has a rho of 0. Let's just do it as 2D. The force vector is Rx, Ry, and the cross product is 0. Then there's the weight force. Rho vector is 0. The force vector is 0, negative 9.81. Cross product is 0. So far, nothing's produced a moment. And then we have the two tensions. So first, the tension touching the 10 kilogram mass. So the rho vector for that's in the negative x direction, is negative 0.050. The force vector is in the negative y direction, T10, so 0, negative T10. The cross product is positive 0.05 T10. Z direction, yeah, all of these are Z components. And then the T20 is positive 0.05, 0. The force vector is 0, negative T20. And so that cross product is negative 0.05 T20. And you can see like this force would make it rotate counterclockwise, so that moment's positive. This one clockwise, so it's negative. Okay, what's the next step? No. That's it. But remember what it is about Newton's second law? When do we use Newton's second law? If there's no fixed point, then we use Newton's second law. If there is a fixed point, we can skip it for now. We might have to come back to it later. But so we're going to skip Newton's second law. because there's no fixed point. Because there is no fixed point. It's not that confusing. It was just confusing because I said it backwards. So if there's a fixed point, and there is in this case, then you skip Newton's second law. Okay, and we go right to the rotational equation. So the moment equation says, 0 plus 0 plus 0.05 T10 minus 0.05 T20 is equal to the moment of inertia, 0.00125 times alpha. Okay, so we can rewrite that as 0.05 T10 minus 0.05 T20 minus 0.00125 alpha equals 0. Call that equation 3. Okay, so before we had 2 equations for 3 unknowns. Now we just added a new equation and a new unknown. That sucks. So now we're at 3 equations, 4 unknowns, 4 variables. But now we have a kinematic relationship that we can work with. So we're going to come up with another geometric constraint that says that the accelerations of, so if you think of the, so the setup is like this, you have an object there, an object there. The vertical accelerations of these are the same as the vertical accelerations of this point and this point, okay? And we know that we have a relationship between the accelerations of these 2 points and the angular acceleration of that body. Okay, so right, and we don't have to. We'll see that all that we want is the vertical acceleration of those 2 points. We don't want to deal with any centripetal acceleration. We couldn't do it anyways because we don't know what the velocity is. That velocity could be anything, but these don't have any centripetal acceleration, so we're just going to skip it, which means that we're only going to deal with the tangential acceleration part of the watermelon equation. Right. So no, centripetal is, remember centripetal, the formula from physics is omega squared r. Okay, so we'll call that A and B. So our new constraint, our last constraint equation, says the acceleration of the point A, y component only, is equal to alpha cross r. This part goes away, this centripetal acceleration. And this has to be equal to the acceleration, 0, A, 10. Okay, so our equation says 0, 0, alpha crossed with the r vector is negative 0.0500. Which is equal to negative, so 0, negative, positive, yeah, negative 0.05 alpha is equal to 0, A10. So our fourth equation says that A10, or let's say 20A10 plus alpha is equal to 0. That's just a reformatting of that y equation. Okay, so now let's substitute this equation into equation 3, and I'll rewrite. I'm going to make one substitution. I'm going to sub A10 in for alpha. And rewrite this as a system of 3 equations for 3 variables. So the first equation said T20 plus 20A10 is equal to 98.1. Nope, 196.2. Second equation said T10 minus 10A10 is equal to 98.1. And the third one, we know that from equation 4, alpha is equal to negative 20A10. So what's 20 times 0.00125? 0.025. Okay, so we have so our third equation says 0.05 T10 minus 0.05 T20, and then plus 0.025 A10 is equal to 0. And the variables are 1, 2, 3, that's all. So 3 equations, 3 variables. And if you solve that system of equations, you can do it with reduced row echelon form or just keep doing it by substitution. But I believe what I have written here is that you get A10 is 3.22 meters per second squared. What did we get for the first one? Oh, I don't have them written, do I? Maybe I do. Okay, T10 is 130, T20 is 131. Right. And so the fact that that the pulley has a moment of inertia now, reduced the acceleration by not a very big percentage. Okay, yeah, 5%. Right. But depending on how much accuracy you need, if you're trying to get like ballpark figure, then yeah, that makes you feel pretty good about neglecting the moment of inertia. But if you need it with a really high degree of precision, then that's something you're going to have to take into account. Mm-hmm. Right. Yeah, depending on what you're using it for, that's definitely true. But if you're trying to calculate where something's going to be at what time, there's no conservative and non-conservative answer. There's just you're right about where it's going to be or you're wrong. Often, yes. Mm-hmm. Yes, that's often true for sure. But right. Mm-hmm. But if you're trying to calculate, like where something's going to be, you need to have a camera looking here at this instant, or then that's different. Mm-hmm. Mm-hmm. Okay, so the question about the mass of the cable, it turns out that doesn't change things very much. Now that I think about it, what you would have to account for. So, what are the other things that you could put into this to get more precision? Yeah. So, what if you added, bearing friction? And cable mass. The bearing friction would just be added on as a couple. So that difficulty-wise, that doesn't change anything. The cable mass, the only thing that would change is you'd have to account for the mass per length of the cable. Then you'd have to think when you isolated. It wouldn't affect the particle free-body diagrams. It wouldn't affect those calculations. You'd still have a T1 and a T2. But this now wouldn't be, or T10 and T20, but this wouldn't be T20 anymore. This would be T20 plus the, let's say the mass, plus the mass of the cable that's hanging there. Same with this over here. This would be T10 plus the mass of the cable 10. And that would all just come from the amount of cable you have there. And then this would be an additional mass. You'd have to deal with, I guess I'll put it in the weight. So this would be M plus the mass of the cable over the top times G. Then you'd still have this force, call that R. And then the process would be exactly the same. So there's nothing fundamentally different about this. You just have to add a few more things in. But, you know, when we went from, I mean, you can see why people want to treat those pulleys as massless, because we had to make a fundamental change to our approach to this problem when we assumed the pulley had mass. You know, adding the other things is really just adding on new terms. It doesn't fundamentally change the way you do it. Cool, right? Oh man, huh. That's too bad. Well, the Pinewood Derby one is going to get you. Okay. We'll do that next time. It's a series of 1-hour lectures on interesting applications. Well, we did
five episodes.
3 episodes, I guess. We did the rolling down the ramp. Now we did this, and next class we'll do the Pinewood Derby. A little different because rolling down the ramp, the only weight force came from the weight of the wheel. Okay? What's going to change? And so when you first think about how a Pinewood Derby, if you're me, you're not, but if you were me, here's what would go through your mind when you first think about it. You think like, well, the Pinewood Derby is just this chunk of wood basically like sliding down the ramp, you know? And so the weight of the thing doesn't matter, like, because if you without friction slide something down a ramp, whatever the mass is, it's gonna go down at the same speed. But then in practice, it turns out the weight of the wood matters very much, and that's why there's a limit to the weight of your car. So what's going on? Well, what's going on is that the force pulling the thing down is mostly the weight of the body, but that the energy from the potential energy of the body is largely going into the rotational kinetic energy of spinning up these wheels. And so what you really want is it's not really the mass of the body that matters. It's some kind of ratio between the mass of the body and the moments of inertia of those wheels. You know, if you could get the moments of inertia of those wheels down really low, you could have a light top and still have it go really fast. But so that's intuitively what's going on, but it's a little tricky to do the calculation. So we'll do that next class. Yes. Yeah. Yeah, that just came up. Did anyone do that this weekend? So, liquid versus solid. I mean, who knows what? There might be really complicated effects of the liquid sloshing around inside. You know, we're doing all this by assuming a rigid body, so I would guess that effect isn't too huge, but those are different in that way. So really the calculation would be for an empty can versus like a can full of something solid enough that it's not moving relative to the can. Pudding.